Good afternoon, everybody. This is Mr. Williams joining you for a redox lesson as we are looking to balance redox reactions. So first, let's look at the reaction between solid copper and silver ions. This is our old standby where you took a test tube, and let's just draw a test tube here. And inside this test tube, you would have placed silver nitrate solution. So the solution would have been filled to this level of the test tube. You then take a copper wire, and that copper wire would be curled and placed inside of your silver nitrate solution. If we let it sit there over time, what would happen is that that test tube would then have the copper ions replaced by silver, and your wire would start to look rather fuzzy. Here was our wire initially, and it would start to grow silver fuzz all over top of that wire. Now, the funny thing about that is that as the copper is being replaced and going into your solution, the solution itself would then start to change colors to our infamous blue color of copper ions in the solution itself. That's the reaction we want to look at first as we're going through this example. So, if we had solid copper, that would just be Cu, and we are going to react that with Ag ions. Now, I know it's silver nitrate, but we're really looking at the net ionic equation here, and it's just going to be the silver ion that is important in this reaction. This is single replacement, but it's also redox. So the copper would now become a Cu2+ ion, and our silver would become elemental silver. The first thing we always have to do is assign our oxidation numbers. So to assign the oxidation numbers in this reaction, copper, because it's an elemental form, would be 0. The silver would be a +1 oxidation state. The copper ion would be a +2 oxidation state, and our elemental silver is back to being 0. Once you've assigned those oxidation states, we will then do half reactions. Why are we even worried about half reactions? Because initially, if we count these up, it looks like we have one silver atom on the left and one silver atom on the right, and one copper atom on the left and one copper atom on the right. But remember, it's extremely important that we both, when we balance a reaction, reactions must be balanced. For both atoms and charge. And the charge is the important part here, because if we look at this reaction, we have a +1 charge here on the left, and we have a +2 charge here on the right. So therefore, although our atoms are balanced, our charges are not. So, how do we write half reactions? Well, the half reactions look at the species that are changing their oxidation states. And in this case, we have copper going from a 0 oxidation state to copper going to a 2+ oxidation state. And we also have silver, which is a +1 oxidation state to start, to silver, which is a 0 oxidation state. Now, when we look at these oxidation states, we have to go through and add electrons to the side of the equations required to make those half reactions equal 0. So in the case of copper, we are going to add our electrons on the product side. Those electrons are being lost in this half reaction. For the silver, we will add 1 electron on the reactant side. And in that case, that electron is being gained. Which one is oxidation and which one is reduction? Well, if you remember back, Leo, the lion, says Gur was one of our tricks for us to help remember, where Leo meant lose electrons is oxidation, gain electrons is reduction. For this reaction, copper is losing 2 electrons. That is their oxidation half reaction. Silver is gaining an electron. That is our reduction half reaction. Now that we've identified it, we have to now balance them. As you can see here, 2 electrons on the right-hand side, but only 1 electron on the left. Those are not balanced. So we have to go through and multiply our reduction half reaction by 2. And by adding it by 2, we will now have 2 electrons plus 2 silver ions, yielding 2 silver atoms. Since our electrons are now both 2, they cancel each other out. And we can take those coefficients and add them back to our original equation. So in front of copper, there is no coefficient, so we will leave that there for being 1. In front of our copper ion, there is no coefficient as well, so we will leave that also to be 1. In front of silver, we have the coefficient of 2. So that 2 will now come up to our original equation and be in front of our silver ion in the original. We also have another 2 in front of our silver metal that we will also put in front of our silver metal in the original equation. If we look at both of our atoms, we have 1 copper on the left, we have 1 copper on the right, so we're good there. We have 2 silver atoms on the left and 2 silver atoms on the right. So we've already balanced our equation for atoms. Now we have to make sure that the charge has been balanced. If we do a sum of all the charges for our reactant side of our reaction, 2 times positive 1 is positive 2. And in the case of our product side, 2 times 1 gives us a positive 2. And so our reaction is now both balanced for atoms and charge. That is the simple redox reaction, including half reactions. But what would happen if we have something that's a little more complex, such as this one? If we looked at the reaction between chloride ions, tin metal, and nitrate, in an acidic solution, we would have the following backbone for a reaction, where we have chloride, tin, nitrate, and then we have a complex tin hexachloride ion and nitrogen dioxide. If we were to first look at this reaction, the first thing we must do is list our oxidation states. Chloride is a -1, so it has a -1 oxidation state. Tin is in the atomic form, so it has a 0 oxidation state. When you have a compound, your overall charge must either be 0, or in the case of this ion, it's going to be a -1, because nitrate is a -1 ion. Therefore, oxygen has an oxidation state of -2, as it's the most electronegative, and its common charge is -2. 3 times -2 is -6. Nitrogen must then be a +5, so that we leave that negative charge on our ion. On the opposite side of our equation, chloride is still a -1. Tin, though, to leave it as a -2 ion, and since there are 6 chlorides, tin must now be a +4. In nitrogen dioxide, oxygen is still -2, as it's still the most electronegative. 2 times -2 is -4, so therefore it is a +4 oxidation state on nitrogen. In any redox reaction, you're only going to have two atoms changing oxidation states when you go to write your half reactions. So our half reactions for this one would be tin with an oxidation state of 0, becoming tin with an oxidation state of +4, as well as nitrogen with an oxidation state of +5, becoming nitrogen with an oxidation state of +4. How many electrons will we need to add to the various sides of our half reactions? Well, for us to have an overall charge of 0, a +4 oxidation state on tin means that 4 electrons had to have been lost. We lost electrons, therefore this is our oxidation half reaction. Nitrogen, on the other hand, has to have the more positive of a +4, and so 1 electron will be added to nitrogen. Since 1 electron is being gained, the nitrogen represents the reduction half reaction for this reaction itself. Once again, if we look at the number of electrons that we have, you will see that there is 1 electron here on the left. There are 4 electrons here on the right. So those are not equal, and we have to make them equal in our half reactions. To do so, we will then multiply our nitrogen half reaction by the number 4 and get 4 electrons plus 4 nitrogens with a +5 oxidation state, yielding 4 nitrogens with a +4 oxidation state. And now, if we go back and look at our electrons, we got 4 and 4. They are equal, and so we can plug those coefficients back into our original equations. So this 4 will go where our nitrate is. This 4 will go in front of nitrogen dioxide, and we can place it like so. 4 and 4. Chloride was not part of our oxidation state, or our half reaction. So therefore, we have to go back to the old way and look at the number of chlorines on each side of our equation. Since chlorine had 6 chlorines on the left, we're going to have to put 6 chlorides on the right. Tins are equal because they're both 1. And now let's count up our oxygens. 4 times 3 is 12 oxygens on the left, and 4 times 2 is 8 oxygens on the right. They don't equal. There's no way for it to equal. We've already balanced our half reactions. So what do? We're in acidic solution. When you need to balance a redox reaction in acidic solutions, we balance oxygen atoms by adding water. And so on our right hand side of our equation, since we only have 8 oxygens and we need 12, we will add 4 water molecules. That now causes our number of oxygens to be 12. But you may say to yourself, we just added hydrogen. What are we going to do with the hydrogens? That's where it's important to know that we are in acidic solution, because acids, as we've shorthanded all year, are H+. And therefore, if we're going to have 8 hydrogens be added to our right-hand side, we will now add 8 hydrogen ions to our left-hand side. And at this point, all of our atoms have been balanced. But what do we still have to do? We need to check the charge. So let's check the overall charge. Here we have 8 pluses and 6 minuses, therefore we're at a -2, and we have 4 more minuses, so we're at a -2. On our product side, we have a -2, and a neutral nitrogen dioxide, and a neutral water, so we're left with a -2 as well. And at this point, we have correctly balanced this reaction in an acidic solution. Both the number of atoms are balanced as well as the charge. But you may be asking yourself, what would happen if the question, instead of said acidic solution, said a basic solution? Let's go back and look at our last reaction, but now it says basic solution. As we finished up, we said that we had 8 hydrogen ions plus 6 chloride ions plus 4 nitrates, needed 4 nitrogen dioxides plus 4 waters to be balanced. That's where we left it, and that's an important part, because anytime it asks to balance in basic solution, don't worry. Balance it in acidic solution first, because that's the easy way to do it. Once you have an acidic solution, we just think neutralization to figure out how we balance it in basic solution. Remembering that H plus OH minus neutralizes to make water, we can use that concept in balancing this redox reaction, because we are going to add 8 hydroxides to each side of our reaction. Why 8? So that these 8 hydrogen ions will be neutralized, because if it's a basic solution, we can't have any acidic protons left. So once we add the 8 hydroxides, we now have 8 waters plus 6 chloride ions plus tin and 4 nitrate ions as our reactants, yielding the tin chloride complex ion plus 4 nitrogen dioxides plus 4 waters plus 8 OH minuses, 8 hydroxides. The great thing about using hydroxide to neutralize the acid is that now we have water on both sides of our equation. As you can see here and here, there's water. There are 8 waters on the left. There are 4 waters on the right. And the idea of Hess's law comes back into play. When you have the same substance on both sides of your equation, they cancel each other out. Now, they're not equal in this case, so we're going to still be left with 4 waters overall, plus 6 chloride minuses, plus tin, plus 4 nitrates. That will give us the tin hexachloride ion, plus the nitrogen dioxide, and now 8 hydroxides. The water has left our product side of our reaction. At this point, we should be balanced for both atoms and charge, but we should check. So we have 8 hydrogens, we have 8 hydrogens. We have 4 oxygens at this point, plus another 4 times 3 is 12 oxygens, so that's a total of 16 oxygens. Here we have 8 oxygens and 8 more oxygens, so that's a total of 16. We're good. We still have 6 chloride ions and 6 chloride ions, 1 tin, 4 nitrogens, and 4 nitrogens. So we are still balanced, in this case, for our atoms. Now let's look at the overall charge. So again, we have to count up the charge on both the reactants and our product side to make sure they're equal. Water is neutral. We have 6 minus here from our chloride ions. We have 4 minus here from the nitrate ions, so that's a total of 10 minus charge. And on the left-hand side, we have 2 minus from our complex ion, and we have 8 minus from the hydroxide. Together, that is also 10 negative charge. So again, this is now balanced for both charge and atoms, and this would be your balanced equation. 4 waters plus 6 chloride ions plus tin plus 4 nitrates yields tin hexachloride complex ion -2, 4 nitrogen dioxides, and 8 hydroxide ions. I hope this helps in redox reactions for both acidic and basic solutions. If you have any questions, you can always talk to me in class. Have a good day.